All right, this question is kind of annoying. We've got 4 different equations here. They're kind of weird format, right? Maybe there's a little bit of a difference between them, but it's hard to know really what's going on just by looking at them. And on top of it, there's a little bit of a trap. So if we read the story and we look at the choices and we think about the types of equations, we can see that we have an immediate choice to make just in terms of the types, right? So A and B are linear equations, right? There's a little y equals mx plus b going on there. Whereas C and D are exponential equations, right? We got a percentage, we've got an exponent, so they're going to behave differently, right? A constant growth is what we think of for linear models. In this case, we constant decrease, but it's the same idea, right? So it's a constant change is a line. Whereas exponential growth or decay is more of a curve, right? It starts slow and then it goes faster. So depending on what the story is saying, we might make a choice one way or the other. So let's just look at it here. It says a photocopy machine is initially loaded with 5,000 sheets of paper. The machine starts a large job and copies at a constant rate. That's an important phrase. After 20 minutes, it has used 30% of the paper. Which of the following equations models the number of sheets of paper P remaining in the machine m minutes after the machine started printing? So if we're comfortable with the terminology, constant rate is going to tell us that A and B are right. One of them is right. Because constant rate is code for line. However, the trap is that 30% of the paper, we normally associate percentages with exponentials. So this feels like a trap. A lot of people fall for this as they see that 30% and they're like, oh yeah, percentages, this is how we do that. And they start making an equation that involves a percentage, which is what C and D are. That's what an exponential really is it's a way of modeling changes that are a percentage. So hopefully we don't fall for that. But it's easy to. And this is a good example of why, if we sense the difficulty of where we are, we know that this is supposed to be a hard question, so we would expect to have to do a little bit of work for it. If we find ourselves looking at a hard question near the end of a section and just kind of coming up with the answer without showing any work on our page, that's not a good sign. It could happen, but it's more likely that you're falling for some sort of trap. We really want to prove our answers here because that's the difference between maybe especially if you're good at math, this is the difference between like a 650 and a 750, is not getting overconfident and using your math skills to prove your answers instead of just letting every little hunch guide you. Because you'll feel really confident as you answer those and pick based on your instincts, but you'll be wrong a lot, and that's a lot of points. So you don't want to be in the habit of trusting yourself on these hard ones. You want to prove it as much as possible. Now, one way to prove it is to recognize that we're given answer choices that are equations. So we would want to plug a point into those equations if we can, because that's one of our strategies that works all over the place. Plug points into equations. So one point that's really obvious is that we're starting with 5,000 sheets of paper. So 0, 5,000 would be a point. However, if I plug 0 into any of these m's, I'm going to get 5,000. A, B, even C and D, because 5,000 times anything to the 0 power, which is what that would come out to, is really the same as 5,000 times 1. So even the exponentials give me the right value here. So that's not great. But we think, okay, there's got to be another point. Now they do tell us that m is the number of minutes and they give us a value for the number of minutes. So presumably 20 is part of my other point. What happens after 20 minutes? It has used 30% of the paper. So let's figure out what 30% of the paper is and subtract it from the 5,000. So that would be, in this case, 5,000 times 0.3, right? That's how we find 30% of 5,000. 5,000 times 0.3. Oh, I could show you another way too. That's going to be 1,500. And then we got to do 5,000 minus 1,500. And that's 3,500. So that's going to be my other point. Let me just show you one other way to get that. We know percentages. Use the open formula, which I've used in other cases on this test. So that's going to be the original amount times the percentage. But since it's a percentage that is decreasing, right, it's decreasing by 30%, we would use 1 minus p, the percentage, to represent what we're losing. And E stands for equals, and N equals the new value. So if my original is 5,000, and 1 minus p is going to be 1 minus 0.30, and that's going to get me the new value. So there we go, 5,000 times 0.7, and that is, I'm just going to do it just to prove my point, 3,500, same value. So both ways are acceptable. The first way I did is kind of more of my instinctual way because I understand the situation very easily, but percentages, remember the point of the open formula is that it works no matter the situation, and it helps us keep track of potential mistakes. So it's good to get in that habit. So now it's just a matter of taking this point and plugging it into the equations. So let's do that. Choice A would be 5,000 minus, let's just zoom in here, 20 times m was 20. So 5,000 minus 20 times 20, which is 400, is going to be 4,600. So that's not the right amount. Remember, we need 3,500. So let's see if this works. 75 times 20. So 75 times 20 is 1,500. And 5,000, it's kind of cluttered, minus 1,500, we already did that before, is 3,500. So there's my answer. Proven. Cool. Now, one thing is, if we plugged that in to choice D, it would work as well, because that's kind of the math we did down here. It's going to end up being 5,000 times 0.7 to the first. So that's a little annoying, but that's why it's really helpful to know what constant rate means, and that we can actually understand from the start that we're really only looking at choices A and B. We want the linear equation. If you didn't notice that, and you needed to figure out another point to test, it's not that hard. You would just need to think, okay, well, if every 20 minutes it loses 30% of the original amount of paper, so it loses 1,500, after 40 minutes, it would be down to 2,000. And we could try that in both of these equations, and it'll work in B, but it won't work in D. So there you go. Whew. Now, look, maybe you would have looked at that and known that that was the answer just through instinct. But I find that very hard to believe. And I could probably come up with another 10 questions, similar questions in the SAT, where you would also have an equally strong instinct and you would get it wrong because there's something else that you're missing. So that's the problem. We don't know when we use our instincts whether our instincts are good. They're going to feel good pretty much no matter what. But that's why we want to prove it, is we know that good instincts can sometimes produce wrong answers, especially on hard questions on the SAT math. So we are preparing for that possibility by being thorough and using strategies to prove our answers. And thankfully, plug points into equations is a very handy strategy that proves a lot of my answers right. I'm very thankful for that strategy. I suggest you get in the habit of using it too.